Okay, last time we finished up with CMOS inverters with a couple observations that the CMOS inverter was sort of a special device or a special circuit because it doesn't consume any power when it's either on or off. It only consumes power in the transitions, and its transfer characteristics are that of an ideal inverter. And we get that by combining sort of the half of the circuit that works best with NMOS and the half of the circuit that works best with CMOS. So they really do, or PMOS. So they really do complement each other and we end up with the best of all worlds. I just wanted to make a couple comments. One is I go back and I clean up these notes, and I will post the notes after every class. I was looking for places where I could maybe improve writing or clarity in certain spots. There will be errors in the notes. If you find them, just let me know. I'll point one out that's particularly egregious because it's a factor of 1,000,000,000,000, and that's when I gave you epsilon naught. Probably a lot of you picked that up. It's not 8.85, but it's 8.85 times 10 to the minus 12. So sometimes these things just don't jump out at me when I'm writing them down, but they do later. So if you find errors, let your classmates and myself know and we'll correct them. But otherwise, I'll try and do a little bit of light editing before I post the notes that go along with the videos. Okay, so we're going to pick it back up again. Scroll a little bit slowly so we don't get horribly nauseated. And we're going to start with looking at MOSFET characteristics in a little bit more detail. And so we're going to call this section, I think this is what the book calls it. We're skipping a little bit ahead to do this because I think it makes more sense to sort of go through operation of the MOSFET all in one shot and give you the complete picture instead of kind of giving you piecewise views of how the thing works. So actual MOSFET characteristics. All right, so we looked at this last time. If we wanted to put a MOSFET into a circuit, we basically have to apply some voltages to get the device to operate in the way that we want it to. And so typically always have to have some voltage on the drain. This is again an NMOS circuit. Almost everything we're going to do is going to be focused on NMOS. And then on the gate, we have to give it some gate voltage that's above threshold so that we form a channel and have some conduction. So we have some VGS. And we said in triode mode, this gives us basically a linear characteristic when we look at the drain current versus drain voltage. It looks like a resistor. Again, this is all sort of a review of what we did in the last one. And we have this other piece of the pie down here on the I = 0 axis where we're in cutoff. If VGS is less than VT, that's cutoff, no current flows. And again, one other observation, I'm going to keep making it because I think you need to get it sort of firmly in your minds. No gate current flows. So in any of these, we're really looking at the drain current ID, or sometimes I'll call this ID or IDS, but they should be the same thing. And again, IG is 0, so we don't have any gate current looking into that capacitor. Okay, so this is the range of operation. We called this triode, and we'll keep using that term. But let's look at what happens. If you look at the graph that we've drawn here, we've really sort of drawn this for low values of VDS. So when VDS is a small voltage. So the question is what happens when VDS gets bigger? And we'll just say when VDS arrow increases. So I'm going to draw the little cross-sectional cartoon, and this one is always a little bit of a bear to get through cleanly, but we'll give it our best shot. So if this is the cross-section of our device, and we have our N+ regions, and I'm going to do a little drawing cheat. Our gate oxide and our gate. So this is our gate electrode. This is our drain. And I'm just writing here that we have, we're applying some VD on that gate. And then this is our source electrode. So this is source, and we're going to say this is 0 volts. And this corresponds to this circuit drawing here, where we basically tied the source to ground. So I'm going to draw this for 3 different configurations, and we're going to look at it, what happens to this picture as we increase the gate voltage, if it cooperates. Okay. So this is my little shortcut that I'll do to make the drawings look consistent. And one more. So we're going to sort of do a high, medium, and low on the drain voltage. So if we think about, and underneath this, I'll do one more little drawing magic. So here we're just going to plot voltage, and we're going to plot it as a function of, if you wanted to call it, we could say that this direction is X, basically looking along that channel from source to drain. And if we plot the voltage, what we would see is that we're going to have some, we're going to assume for one, we're above threshold, and never give myself enough room. So we're going to assume we're above threshold. So VGS is greater than VT. So we'll draw something here that says VGS. So again, this is some arbitrary voltage that's above threshold. And we'll say it is that much above threshold. So VT is going to be here. And we can just sort of trace that over to the point where, if we again wanted to label this as X, this would be X equals 0 at the source and X equals L, the channel length at the drain. And then so at the drain, if we sort of plotted the voltage VGD, so the voltage at the the voltage at the gate relative to the voltage at the drain. If VDS, let me do a little copy paste first. So we're going to fill this in again for all of the cases we're going to consider. You know, just try and mostly keep it consistent. Okay, so if we started out, and if we said that VD was equal to 0, then the channel underneath, so the voltage between the gate and the channel is uniform, because there's no difference in voltage between VD if VD starts at 0 and the source, which is at 0 volts. So we would have a uniform channel. And that would be true as long as VDS is small. So what we could do is we could say, all right, VGD, if VDS is small, we would have, drawing tool's got to cooperate. We'd have to have, so let's say that's our voltage changing. So the voltage at the, let me just annotate it and I'll go through it. So when VDS is small, what we end up having is VGD. So this will label as VGD. And this voltage difference is VDS. And so basically, we have a healthy amount of voltage between the gate and the drain. And so there's a large, a healthy channel, a lot of charge that's produced even at the drain. But what happens is, as we start increasing VDS, then we start seeing a bigger difference between the voltage at the drain relative to the source. And so that starts eating into the voltage difference that we have between the gate and the drain. And so this again remains, actually, what am I doing here? This, I don't want to label that point. So this is VGD, and this is still VDS. So as we start increasing the drain to source voltage, VDS, now the difference between the gate voltage and the drain voltage becomes higher and higher because we're sort of subtracting whatever voltage we have at the drain from whatever voltage we have at the gate. And so we continue, and if we wanted to draw this channel, so again, this channel is N-type. So now instead of having a uniform channel, we start having the full channel at the source side and a relatively smaller channel at the drain side because we don't have as much voltage difference between the gate and the drain to produce as large of a channel. So if we go to the kind of extreme point, well, not fully extreme, but one interesting point is where we have just barely a threshold voltage between, so this is VGD, and this is still VDS. So what's happened here? At this point, we've increased VDS to the point where the difference between the voltage at the gate minus the voltage at the drain is only equal to the threshold. And so that's that statement right there. So at that point, if we think back to how the channel was formed, we basically said that we needed to have a threshold voltage, the magnitude of a threshold voltage, to form a channel at all, if we wanted to be above cutoff and have current to flow. And so when we get to the point where there's only a threshold voltage between the gate and the drain, we basically are just on the edge of having any kind of channel whatsoever. And the way I've drawn this, maybe I'll just, because it looks a little misleading, it looks like we're getting more and more channel at the gate, which is, or sorry, at the source end, which is not correct. So this one, let's just say we're sort of pinching. Probably as painful to watch on video as it is for me to try and do it. And then on the uniform side, we'll just make it thicker so that we can sort of illustrate more what's happening. So at this point, when we've only got a threshold voltage between gate and drain, we say that the channel is pinched off at the drain. And so what happens here, and we're going to sort of draw it in an IV characteristic, but what happens at that point is that the resistance of the channel, the difference or the resistance between drain and source goes to effectively infinity. But the confusing part that you sort of have to think about a little bit is that the current will still flow. So the current just clamps, even if you increase the voltage above, from drain to source above this point where you pinch off the channel. And the reason why that happens is you still have a lot of electrons that are in the source that get injected into the channel. They still see the voltage between the drain and the source. And so that voltage pushes them through the channel, but effectively the resistance of that channel goes to infinity. So it's kind of a concept that takes a little bit maybe of imagination to get your head around how if there's infinite resistance, you can still have current flow. But that's really the heart of using the MOSFET in the next range of operation that we're going to talk about, which is called saturation. It ends up looking like an ideal current source. So if we take those next steps, so we just sort of described graphically and hopefully somewhat straightforwardly. Let me just make sure what we're really doing here is VGD. Okay. So this is sort of what happens inside the device. If we looked at the MOSFET characteristics now, and we're going to draw this over and over again. So this should be something that in the next couple weeks you guys have memorized is how these IDS, VDS characteristics look like. So far we've only really looked at this part or this curve down close to the VDS equals 0 or the low VDS regions. So I'm going to give a little bit of a preview on where we're going to go next. But there's basically a boundary that happens between these two modes of operation, the triode that we've talked about before, and that happens sort of down when VDS is low. And then we transition and we move into this saturation region, maybe. So we move into the saturation region, and what happens is that transition point where, so if I just wanted to start labeling these, so triode is that lower VDS region, and saturation is this new mode of operation that we're talking about. So what happens is when we really only have that one threshold at the drain to, or gate to drain, sorry, that's the boundary of this region. And so we could say that what really happens there is that VGS is equal to VDS plus VT. And that's what we've drawn here. So VGS, the full voltage, is equal to VDS plus VT. So that's how we've sort of drawn this. And what that means is we could just rearrange a little bit, and it will be the criteria that we use to determine which side of the boundary that we're on. So this is really VDS equal to VGS minus VT. So this is going to be our critical criteria to know whether we're in one of these two regions, triode versus saturation. And again, if we I'm going to hammer that one home. That line, and I'll show you how we get to that parabola. This is VDS equal to VGS minus VT. Okay, there's one other condition that has to be met here for operation in either region, because we still have, and I'll just make it a little sloppy so we see that there's a line there, but we still have to have VGS greater than VT to have any current flow. If it's less than VT, we're still in that cutoff mode of operation and no current flows. And again, what I said a second ago is true. If you look at the saturation regime, so here, this characteristic looks like an ideal current source. And this is one of my pet, I don't know, issues if you want to call it. But I try and hammer into these classes what an ideal current and a voltage source look like. So we're going to go off on a little bit of a tangent here, because I think it's important to just sort of have that in your mind. So ideal sources. So hopefully we understand what that means, that it looks like an ideal current source. So if we have an IV characteristic, or let's draw we'll do voltage first, even though we brought up current. So if we have an ideal voltage source, and we would model that as some kind of a voltage source and some kind of a parallel resistance. You could think of this as your Thevenin equivalent of a voltage source. For an ideal source, this resistance is equal to 0. And what that means is, if you look at the IV characteristics of an ideal voltage source, so this is V, and this is, sorry, let's do I and V in the right order. This is I. So we want to look at the current produced as a function of the voltage. So an ideal voltage source means that if we set the voltage to some voltage V, we will get whatever current that's required to produce that voltage. So the IV characteristic ends up looking like this. An ideal current source has 0 resistance, and you could convince yourself the slope of that is infinite, so 1 over the slope would be 0. And again, whatever voltage you're going to ask of an ideal voltage source, it will produce via whatever current has to happen to make that voltage work. The other side of the equation is an ideal current source. So this would be your Norton equivalent. So if this is some I, maybe we would just call that V naught. We set it to some voltage that we want, and it'll give us whatever current is required. So on the current source side, it's just the opposite. So for an ideal current source, we want an infinite amount of resistance. And what that means from the IV standpoint, if we wanted to just draw its characteristics, we would have a kind of orthogonal picture to the ideal voltage source. So now if we want to set this current source equal to some value I naught, it's going to give us that current, and it will go to whatever voltage it has to across that current source to produce that current that we're desiring of it. So in this case, again, this is R is equal to 0 for an ideal voltage source, and this is an infinite resistance for an ideal current source. And the sources you use in the labs are relatively ideal. So you can think of, if you're using a power supply, that's basically an ideal voltage source. It'll give you as much current as it can until something pops or blows up. So in the mode of saturation, we can sort of look at it and identify that this part looks like an ideal current source. We have some current that's flowing, and it's dependent, we'll get to that one in a second, it's dependent on what the gate to source voltage is set to. That's how we control the level of the current. And it looks like an ideal current source in that the resistance is infinite. So it doesn't matter, another statement or another way to say that is, it doesn't matter what VDS we apply, as long as it's bigger than this criteria, so bigger than VGS minus VT. If we apply a VDS greater than that, we will always get that same current, unless we mess with a VGS. So if we, for a constant VGS, we will always get the same IDS current as long as VDS puts us in the saturation region. Okay, so what we're going to end up doing is we're going to break this up. So it's most useful to use a MOSFET in either one of these distinct regions. So either sort of solidly in the triode region or solidly in the saturation region, where they basically operate near ideally in terms of looking more like a resistor, looking more like a current source. So we'll show you in a minute, again, a model that sort of unifies this full ID VDS characteristic. I guess what I can add to this is, let's maybe add one more curve, and let's add a couple more. So these would be for different levels of VGS. So you'll sort of see these drawings for MOSFETs, and it never goes negative resistance. You'll see these kind of drawings for MOSFETs. And you could look at it, and it would make sense, I think, in both of these modes of operations, is these family of curves that I've drawn, this is as we increase VGS. So we'll see it in saturation, but we could also think about what we've already done in triode. So in triode, we made the observation that the on resistance, R on, is inversely proportional to the voltage VGS that we apply. So the higher level of VGS that we apply, that resistance goes down. And so these curves in triode become more steep as we increase VGS. And in the saturation, we'll quickly find the equations for it. I'll write it down in a second, but basically we get a similar effect in that as we increase VGS, we will increase the drain current in the saturation region. So again, the gate electrode becomes a very important control for what's happening between the gate, or between the drain and the source. And I did add one annotation to the last set of notes, is that digital systems, and you could think of the inverter that we talked about as an example of a digital circuit, they tend to have high VGS and low VDS. So they tend to operate in the triode region. And we can just maybe say that because we're going to break this up into two piecewise linear regimes. So again, I added this on the last page of the last notes, but digital systems, they tend to, and again, let's think of that as what we've already talked about, an inverter. These operate with high VN or high VGS. And so those are in the triode mode of operation. And in that triode mode, we use the SR model. And what we're going to talk about for really the next couple of lectures would be more analog amplifier applications. And so analog systems, we operate at higher VDS, lower VGS, and so these are in saturation. And we're going to use a new model that we're going to do right now, which is the SCS model. So what we basically want to do is break up this kind of complicated looking characteristic that looks nonlinear. It's got these two different modes of operation. Again, we sort of typically want to operate solidly in one side or the other of that mode of operation and not in the gray zone between triode and saturation. So what we do is we want to break this thing up. And so we say when we're solidly in the triode mode, we will use this SR model. So we'll have this linear resistor. And then we'll be aware that there's some boundary. And when we're in the saturation side of that boundary, we will treat the MOSFET as a perfect current source. And so we basically just produce whatever current we dial in with the gate source voltage, and we get an infinite resistance, just like a ideal current source would look like. And so this is the SR region. This is the SCS model. And again, SCS, this is saturation. I'll say sat, and this is triode. Okay, so what do we mean by this SCS model? Maybe I can leave it there for a minute so it's visible. This again is IDS, VDS, and these would be for increasing VGS. And again, never forget about our friend cutoff. It's important when you use the MOSFET as a switch to be able to turn it off. Okay, so SCS current circuit model. The handwriting lesson. Okay, so in this mode of operation, we're basically going to look at, well, for one, I guess I could spell it out. So what does SCS stand for? So it stands for switch, current source. And so what does the device end up looking like? If we wanted to draw it in the two modes of operation, so when we're in saturation, we're either going to be in saturation, where we're operating at some VDS where we're in the saturation mode, or we could still be cut off, depending on what we do with the gate voltage. So, of course, our device hasn't changed. We're just operating it differently. So our circuit symbol stays the same for this NMOS device. But we have two different modes of operation. So one is this cutoff mode. So if we have our gate and we have the drain and source, the gate's really that control electrode. And I'm going to remind us here, no gate current, but we also have no drain source current flowing. And so this is our VGS less than VT. So we haven't turned the device on. So this is cut off. But then we can actually turn it on in saturation. And when it's in saturation, we have a dependent current source between drain and source. we still have a gate electrode, which is doing an important control function, but no current is flowing. And in this situation, we model that dependent current source, and we could write it to just say, to remind ourselves that it's a function of VGS. So it is not a function of VDS. And that's our statement that says it looks like an ideal current source, where no matter what, if we look at any one of these, as long as we're above that saturation cutoff, it doesn't matter what VDS we put on, we still have an infinite resistance and the current does not change. So it's only a function of VGS and not a function of VDS. And the actual function is k/2 VGS minus VT, and it's quadratic squared. So what does that tell us? It tells us, and I'll tell you what K is in just a second. K is a constant, and so it basically tells us that if we increase the gate to source voltage, and it better be above VT anyway to even be in this mode of operation. We should write that down. VGS greater than or equal to VT. So we know it's that term in parentheses is greater than 0, and basically as we crank up the gate to source voltage, the difference between it and threshold gets bigger, so the quantity in the parentheses increases, and then we square it, and so we have a large increase in drain to source current, and it's controlled by the gate electrode. So that's maybe another way to think about it is IDS, let's call it magnitude so we know what we're talking about. Controlled by VGS. And again, that's what makes these useful devices is you have a third terminal that really controls the action or the current in the other two terminals. Okay, so in this mode of operation, we could look at it. For one, we could plot a different way of looking at current voltage, just switching out and saying, all right, we're interested in IDS, sorry, inadvertent scroll. So we could, instead of plotting IDS versus VDS, we could look at IDS versus VGS. So this kind of tells us the amount of control we have of the drain current, drain source current with the gate terminal. So for one, we could say we know what the answer is below this critical threshold point. Below that VT, we have no current. So we get nothing. So all the action is going to happen when we get VGS above VT. And then when VGS gets greater than VT, we're going to have this parabolic or this square increase in drain source current. And this is going to happen as this k/2 VGS minus VT squared. And yeah, so the corresponding, which we've already kind of drawn it, but just to remind us that these two things happen, we're plotting two different dependencies when we either plot IDS VDS or IDS VGS. So this mode of operation, again, these equations are only valid once we're in saturation. So here, this is triode, they don't work. It's a different mode of operation for the MOSFET. And then over here in saturation, sometimes they snap. Here in saturation, we have this constant current source, and as we increase VGS, we get higher and higher drain source current. And again, just to hammer these things home, this is our VDS equal to VGS minus VT boundary. And if we wanted to look at it along that boundary, so if this is our boundary, triode and saturation. Okay, so at that boundary, we know, I just wrote it, but I'll do it again. VDS is equal to VGS minus VT. So if we knew that IDS is K over 2 VGS minus VT squared, can plug this straight in and say that we get K over 2 VDS squared to describe that parabola and that boundary between triode and saturation. So that's why it ends up looking like that parabolic shape. Okay, so let's summarize this thing and then I'll say a couple words about this K constant. So we sort of looked at the equivalent circuit elements that we would use either in cutoff or in saturation mode. We looked at the IVs, and so we can just basically write down our rules for the current. So our IDS current is going to be K over 2 VGS minus VT squared. And our conditions to get there, first one, have to turn the device on. So VGS has to be greater than or equal to VT. And our second is our new criteria that we're going to use extensively. So VDS has to be greater than or equal to VGS minus VT. And if we are not above threshold, we get no current. So VGS less than VT. So that is our SCS switched current source model. Let's spend a second on K. So we could do a units analysis, which I always like to do. If we looked at it, we have, so IDS is equal to K over 2. And then just from a unit standpoint, what's VGS minus VT? That's voltage, and then we square it. So this has units of volts squared. So we could look at it and say, all right, what units does K have to have? Well, K would have to have units. We know the IDS is amps. We'll say milliamps just because amps is a big number, and for MOSFETs will usually be in the milliamp regime. So we can look at it too as unitless, it's constant. So our units for K have to be milliamps per volt squared to get things to work out. And how do we get to those units? Well, so a lot of times we'll break up this K, and I'll try and be very clear when we're going to use an overall K or we're going to break it up as follows. So a lot of times we will say we're going to call it KN, N for NMOS, and we'll give it a prime, and then we'll pull out two features, two dimensions of the MOSFET itself, which is what we drew in the last lecture, W over L. And because again, if sometimes we had a PMOS or an NMOS, we may choose to subscript these with an N because we're in the world of NMOS here. So this is useful to do this because Kn, you could think of this Kn prime part as a constant depending on the technology, or equivalently process. So this is going to be something that's kind of inherent to whatever fab is building the MOSFETs that you're using. And so that's typically a given quantity. So this one, if you wanted to know what was in that constant, so Kn prime is really, you could break it up into mu, which is mobility, times Cox. So mobility is just a property of the semiconductor. Depends on doping, depends on the semiconductor itself. You will learn more about this in ECE1032, mobility. And this units are centimeters squared per volt second. And so it basically relates the velocity to the electric field that's applied. And this one, Cox, is the MOS capacitance per unit area. And so this is really, again, this is dictate or set by the process. And what does that mean? This is the thickness of the gate oxide. And the dielectric constant of the gate oxide. Call it gate oxide. Okay, so why is it useful to sort of break it up in this way and think about this technology or process dependent part and then the W over L? Well, if you're designing a MOSFET as a circuit designer, you have control over W and L. You can draw whatever you want. So these are design variables. So you can sort of tune the MOSFET to do what you want it to do by changing the ratio of W over L. And by doing so, you can sort of tune MOSFETs to have higher or lower current drive just by making the physical dimensions of the device different. But whereas that Kn prime, that's just set by the technology. So in some problems that you'll be doing in homework and exams, I will give you an overall K. So if I just give you a K value, assume it's got everything baked into it. So it's going to give you the overall sort of properties of the MOSFET. If you get a Kn prime value, then I'm probably going to be asking you more about what ratio of W over L you might need to solve a given problem. So try not to get confused with that, but it is kind of useful to separate that K constant into these two parts, one of which is really set by the technology, the other one is in your control as a designer. And Kn prime, this will be given. I won't have you calculate that. This will be a given parameter. Okay, so let's do a quick example and say, how would we use this switch current source model to solve a problem? This is out of the book. And I don't know that I've said it yet, but I would encourage you all to read the book. I have somewhat mixed feelings about the book, but it's definitely better than nothing. And I'm basically following a lot out of the book. So it's a good way to reinforce things that we talk about here. All right, so if we draw, yeah, let me say one other word here too. So I'm not going to be completely consistent with the way I draw circuits. And that's sort of by design, because I think it's important that you get kind of comfortable with seeing them multiple ways. So just as an example, I can draw this circuit this way, or it doesn't change anything if I explicitly draw all of those grounds connected. So just keep that in mind and try and get comfortable with these different ways of looking at circuits, because not everybody draws things in the same way. And so it's kind of important to figure out how to interpret people's different graphical preferences. So if we have this circuit, problem will be, let's find the drain source current. So we want to find IDS, and we're given, let's do VD, 5 volts on VDS. Let's call K equal to 1 milliamp per volt squared. Threshold is 1 volt. And let's say we know that we have VGS equal to 2 volts. So first questions. So that's what we want to do. Find the drain source current. So first question is, what mode? So we could say, what's our first check that we want to do? Well, for one, we better make sure the device is on. So we can check to make sure that it's not in cutoff mode. We do that easily. We say that VGS is, our check is VGS greater than or equal to VT. And we can say VGS is 2 volts, VT is 1 volt, so absolutely check. So it's not in cutoff. Then our next criteria is we need to know, is this in saturation or is this in triode? And so that criteria is VDS greater than or equal to VGS minus VT. And that's written as a check to see if we're in saturation. We could also write it as a check to see if we were in triode. So where are we? VDS is 5 volts. Is that greater than or equal to 2 volts minus 1 volt? And the answer is yes. So this tells us we are in saturation. And so if we're in saturation, then we know that we can use the switch current source model. And one other aspect to this question is what would be the minimum voltage for us to be in saturation? And so just right here, as we've applied that criteria, we would say that the minimum voltage, and by minimum voltage, I mean minimum VDS for saturation, is just going to be VGS minus VT. So that's going to be 1 volt, 2 volts minus 1 volt. And we could say, what's the maximum VGS for saturation? So the minimum VGS is what we already said, is it's got to be greater than or equal to VT or we get no current. So we know that one off the bat. What's the maximum VGS for saturation? Well, if we still have to say VDS is greater than or equal to VGS minus VT, and we know now that our maximum VDS is 5 volts. So if we plugged in 5 volts for VDS and VGS is 1 volt, we could say that VGS has to be less than or equal to 5 plus 1 or 6 volts. So as long as we have VGS above cutoff, or above threshold, so 1 volt up to 6 volts, we would be in saturation, and we need at least 1 volt of VDS to keep that device in saturation. So now we sort of know the regions of operation for keeping this device in saturation. We know that with the parameters that have been given, it's in saturation. So then what do we use? We use the switch current source model. All right. And we can just straightforwardly draw that in. So we have some VGS. The gate's just a control electrode. Let's give ourselves more room. The MOSFET just becomes our dependent current source. And this one is K over 2 VGS minus VT squared. And we're connecting that up to some VDS. So what's that drain source current, which this is IDS. So we can just, so IDS is equal to, start plugging things in. So K was 1 milliamp per volt squared. We have a factor of 2. Yeah, let's not even write the units. I think we went through that unit analysis, but keep track of them. Always a good idea to make sure your units are right, because if your units aren't right, your answer won't be either. So VGS is 2 volts, VT is 1 volt. We square 1 and we still get 1, and so we can say that IDS is equal to 0.5 milliamp. And again, that's where the units are important, because K, it's not amps per volt, it's milliamps per volt. So it's kind of trivial, I will definitely admit that, but it's important to kind of go through and get the right picture of which mode of operation the device is in. Because if you don't check that and you assume that you are in triode and solve the problem, you will get the wrong answer. And I'll hammer this one home as well too, but basically, if you don't know what mode of operation the MOSFET is in, say, I'm going to assume it's in saturation, solve it using the equation for the drain current and saturation. And once you've solved it, then you can kind of go back and check the voltages and see if they still make sense. That doesn't really apply for this circuit, because here we don't have any resistors. There's sort of nothing that can change. When we have ideal voltage sources on VGS and VDS, it's clear that that current's going to flow, and the mode of operation is trivial. We just subtract the voltages appropriately. But if we have more complicated circuits, then you really need to check, assume the mode of operation, find an answer, and check it to make sure that your assumption is consistent with your answer. And if you do that, you will always get the right answer, assuming you do the math right. Okay, so I think the next one we're going to do is just this will sort of tie a bow on the operation of the MOSFET and the different modes. And so we're going to present here yet another model for the MOSFET. And this one, maybe it's a little bit more satisfying because it's a complete model. There's no sort of discontinuities in this piecewise linear. It'll model the IDS versus VDS current over the full range of operation. But again, it's not something that we necessarily always have to deal with, because we typically want to stay in triode or saturation. So I think this is section 7.8 in the book. We're going to call this the switch unified MOSFET model. All right. So in saturation, this model is not going to change. It's going to still model the MOSFET as an ideal current source. What's going to change is our equations for the MOSFET in triode, so that we, again, have a continuous set of IV characteristics. So if this is our IDS VDS curve, we can add in that parabolic boundary. And so what we're going to do is, I guess I'll just write the equations. So in this model, now we're going to have a more complicated formula for the drain source current in triode. So we'll start with that one. So we have K, same K that we just talked about. We have a VGS minus VT times VDS minus VDS over 2, VDS squared over 2. And so there's triode. Saturation, we'd have K over 2, same thing we just did, VGS minus VT squared, and cutoff 0. So there's the other criteria that we have to check here. So in triode, we know that VGS is greater than or equal to VT. We turn the device on, but VDS is less than VGS minus VT. In saturation, we know that the device is on, so VGS is greater than or equal to VT, but VDS is greater than or equal to VGS minus VT. And in cutoff, that one's easy. We just know that VGS is less than VT. So we could sort of delineate these modes. This is triode, which is the only thing new about this model. The middle one is saturation, and the bottom one is cutoff. Okay, so what this is going to give us is a characteristic that looks like what I drew earlier, where we sort of come up and then we have a ideal current source behavior in saturation. So again, what we changed was triode. So let's take a little bit closer look in triode. So we can check a couple of things. So one is what happens between the triode and the saturation boundary. So if we started with our new, more complicated expression for drain source current in triode. So we know at the boundary, and that's the boundary between, I'll just say it, between triode and saturation. Our condition at that boundary is VDS is equal to VGS minus VT. And so if we just straightforwardly plug that right into our expression, we can say IDS is K VGS minus VT. I won't skip steps just to be very explicit, minus VGS minus VT squared over 2. And again, here all I've done is just substitute VGS minus VT for VDS. And that whole thing is multiplied by K. So we just plug that in. So we can look at it. The first term, we have a VGS minus VT squared minus a VGS minus VT squared over 2. So lo and behold, it gives us the exact same equation at that boundary point that we would get with the saturation current expression. So what does this tell us? This says that the current is continuous. At the boundary, which is a good thing. That tells us we do have a unified model that can predict that drain source current over that full range of MOSFET operation. But the other one we might want to look at is the effective resistance of the MOSFET. So if we consider RDS, call it a little one, not that it matters. So if we consider the drain to source channel resistance, we could say that RDS, if we wanted to find it, we could, well, I mean, ideally we would just say it's the incremental change in VDS, I guess those are just these, divided by the incremental change in IDS. But we're typically plotting it I versus V, and so this is the same thing as 1 over that slope of the IV characteristics, which is DIDS dVDS. So we could look at this one of 2 different ways. If we go back to that original equation, so we could say, I'll just write it so it doesn't get, if we had, this was our equation, so we could say that in triode, we know that VDS, so we could make the observation VDS is small. And so if VDS is small, we could maybe say that we could just neglect that VDS over 2 term, because but VDS squared over 2, because we're multiplying a small VDS times a small VDS, it's going to be a very small number. So if we did that, which this is just sort of illustrating 2 ways to look at this. If we did that, we totally neglected that term, and we took the derivative of IDS with respect to VDS and did a 1 over, we would say that RDS would be equal to just that K VGS minus VT. And this one, this is just important to note. This is the same thing we were talking about. We're in triode, so this is what we called our on in the SR model for the MOSFET operation in triode. But if we didn't want to just do that neglecting operation, we could just take the derivative of the drain source current with respect to VDS. And so if we did that, if we had d/ds, maybe we should break that because this is sort of a different consideration. So d/vds, if we just take that derivative, we end up with k vgs minus vt for the first term, minus vds for the second term. And so again, in triode, this is equal to 1 over r on. And I keep saying triode, we haven't left that. We're always considering it in triode here. But now if we wanted to know what happens at the boundary, so and again, at the boundary means at any point along that parabolic curve. So if we wanted to remind ourselves what that looks like, it's true at any point along that boundary. And we know there again, VDS is equal to VGS minus VT. If we plug that into the derivative that we just got, or we could just, I'll write it one more time just to make it a little bit more insightful. We could say this R on that we're getting is 1 over K VGS minus VT minus VDS. So that's true, that's just the derivative. But then at that boundary, if we plug in VDS equal to VGS minus VT, this goes to infinity at the boundary. And it stays at infinity beyond the boundary. So when you're in saturation, and again, I'm just going to remind us of this, in saturation, we have IDS equal to K over 2 VGS minus VT squared. And if we took, if we took DIDS, DVDS, it's 0. So this also predicts R on, it's not R on, we'll call it RDS in saturation. RDS goes to infinity. And that's just another statement that in saturation, the drain source voltage has no impact on the drain source current. It acts like an ideal current source with infinite resistance. Okay, so that's, again, the last, this sort of, we're going to transition out of these discussions of models, and definitely in the next class or next lecture, we're going to talk more about circuits and start building amplifier circuits using these models. So again, I think it's comforting to know that there is a full unified model that can accurately predict these families of curves that we get for the MOSFET. But by and large, for most purposes, we are not going to be using this unified model. We'll either stick with triode, where we model it as a switched resistor, or as a switched current source in saturation. Having said that, we'll do one quick example here. So let's use this unified model. I think this is also from the book. So let's say we've got 2 different transistors. So we've got M1, and you'll see the transistors labeled that. It's probably obvious why it's M. My guess is it stands for MOSFET. So we've got 2 of these transistors stacked up. We've got some output voltage, and we've got a 5-volt supply connected to the gate of M1. And we've got a 2-volt supply connected to the gate of M2. And I'll, again, keep writing these until I'm going to stop soon, where we all know what the gate, source, and drain are in these circuits. And so the question is, given M1 and M2 are in saturation, what is V out? So actually this doesn't use I thought we did have an example that used that unified model. You can do it, it's just a little bit more ugly because it's got those extra terms in it. So this is another example of saturation. We're given that both of these devices are in saturation. We want to calculate what that, I guess it's not an out, be consistent. What is VO? Well, we need to know the properties of the MOSFET. So we're given that K is 4 milliamps per volt squared. VT is 1 volt. And so we should have all the information we need to find this. We don't know what VO is, and so VO, in this case, we can just look at it from the circuit. This is equal to VDS2. So we couldn't really know whether M2 was in saturation or not until we find that voltage, but we'll find it and then we'll go ahead and check it. So if we're given this information, we're going to use SCS. And so we could redraw that circuit. Oh, and there's a 10 volts up here. We do need that. So our supply stays the same. We end up, if they're both in saturation, with 2 dependent current sources. There's our VO. And then the gates, this one is at 2 volts. This one is at 5 volts. All right, and so how do we do this? Well, if we look at that circuit, I think there's one critical observation is there's not 2 different currents flowing. There's not 3, there's not 4, there's one current. There's only one path for current to flow. And I think a lot of us are used to thinking of currents in terms of loops. And so I'll just tell you, you could draw it if this isn't obvious. I could always redraw this circuit this way. And so here, if that helps to make it more obvious that I do have a loop for current to flow, or a path for it to flow, you can always sort of expand that circuit and show it if that helps in any way. So if we make that observation that those 2, so this was M1, so IDS1 and IDS2, those have to be equal to each other because again, there's only one current flowing. So for M1, we would say that we'd have a K over 2 VGS1 minus VT squared. And that's going to have to be equal to K over 2 VGS2 minus VT squared. So we can cancel a couple of things. The K's go away, K over 2's. We can cancel the square roots. And so we end up with VGS1 minus VT has to equal to VGS2 minus VT. And this one, if we just took a step back, that's the mathematical statement. But if we looked at it, we could say that from the information that we're given, K is the same for both of those transistors. That's why we're able to cancel it in the equation. So if K is the same, then for that transistor to produce the same amount of current, we would have to have the gate source voltage be greater than VT by the same amount for both of those transistors to give us the same value of, again, drain source current. So they have to be, this relationship has to hold. Thresholds are the same, so now we can cancel those. And we can say that, again, gate source voltage for number 1 has to be the same as gate source voltage for number 2. And so then we could just say, all right, straightforwardly, we know what the gate source voltage is for M2. We can just say that we know that the gate is biased at 2 volts and the source is held at ground. So VGS2 is 2 volts. So now if we know that VGS1 is 2 volts, we don't know what S1, VS1 is, but we know that VG1 is at 5 volts. So if we know that I'll just be very explicit, VGS1 1 has to equal to 2 volts, and this is equal to VG1 minus VS1, we would say that VS1 is equal to VG1 minus 2 volts, which is equal to 3 volts. So V out equals 3 volts. Now, as a final check, this was the comment that I made earlier, is we assumed a mode of operation. We got an answer. It's a really good idea to always check that your assumption of the mode of operation was correct. So let's do that for both of those devices. So let's call this our mode check. So for M1, we're going to have to apply the criteria. We want to be in saturation because that's where we were told to be. So our saturation criteria is VDS1 greater than or equal to VGS1 minus VT. So now we know what VGS1 is. We did that before. This was 2 volts. So this is 2 volts. This is 1 volt VT. But what's VDS1? So we found it, VDS1, we found that VS1 is equal to 3 volts. The voltage at the drain for M1 is equal to 10 volts. So we have 10 minus 3, we have 7 volts. And so lo and behold, that's a check. This is in saturation. For M2, same criteria, VDS2 has to be greater than or equal to VGS2 minus VT. So again, we know VGS2 minus VT has to be the same as for M1. It's 2 minus 1. So this is greater than or equal to 1 volt. And VDS2, that's just equal to V out. That's what we just found, or VO. And so this is 3 volts. Is that greater than 1 volt? Yes. And so again, we can say that we are in saturation for both of those devices. Our original assumption held true. And so we have high confidence that we got the right answer, again, assuming that we did the pretty simple math in this case correctly. So I will leave it at that. Again, I think what we've done in the first 2 lectures are we've sort of covered the basics of the MOSFET's operation. We've gone through triode, we've gone through saturation. We presented that unified model that we won't use quite as much. The next time we will dive into looking at how to build amplifier circuits with MOSFETs. And so that'll be more chapter 7 in the book. I would encourage you to go ahead and read it and prepare for it. And we will start in on that one the next time. Thanks.